Welcome everybody. So it's a pleasure for me to introduce you CEM TEKIN today. CEM TEKIN is an assistant professor in the Department of Electrical and Electronics Engineering at Bilkent University, Ankara. And he received his PhD degree in Electrical Engineering Systems and MS degree in Mathematics and MSc degree in Electrical Engineering from the University of Michigan. He received his BS degree from our university, Mills Technical University, from the Electrical Engineering Department. And from 2013 to 15, he was a postdoctoral scholar in Electrical Engineering Department at UCLA. CEM has authored or co-authored over 50 research papers, 5 chapters, and a research monography. He received several awards in his career, including the Best Paper Award in Bilkent 2009, Distinguished Young Scientist Award, and Pareto Foundation Young Investigator Award in 2019. His research interests include bandit problems, machine learning for personalized medicine, multi-agent systems, streamlining, influence maximization, and cognitive communications.
So thank you very much for the kind introduction and also inviting me here to give a seminar. Today I will talk about how to trade off exploration and exploitation in sequential decision making in complex domains. In particular, I will focus on how to learn under the presence of multiple and possibly conflicting objectives and contexts. So many complex engineering applications like personalized medicine, intelligent transportation, recommender systems, influence maximization, social networks and telecommunications require making real-time decisions and online learning under the presence of diverse and high-dimensional features. So these problems are further complicated due to existence of large strategy sets and multiple and possibly conflicting objectives. So in this talk, I will explain methods and algorithms that will be able to achieve guaranteed performance, fast learning, fast decisions, and fairness in these complex domains. So here is the outline of my talk. I will first motivate multi-armed bandits for sequential decision making. Then I will motivate bandits for how to model sequential decision-making problems in complex domains. After that, I will present a particular bandit problem called multi-objective contextual bandit. And I will talk about how to achieve different notions of optimality, including lexicographic and Pareto Optimality. And I will conclude by some feature research directions. My presentation will include some pieces from the recent works of me and my students. For the details, I would like you to take a look at these works. So I'll start by introducing the bandit problem, which is basically a sequential decision-making problem under uncertainty. So this is a reinforcement learning problem, where the decision maker proceeds over rounds indexed by t. We assume that the decision maker, the learner, at every round selects one of the k arms, and each arm generates a random reward that comes from a fixed but unknown distribution. So at round t, the learner selects an arm, it receives that random reward. This is called bandit feedback, because the learner only gets to observe the reward of the arm it selects. It doesn't observe the rewards of the arms that are not selected. So, in this model, the goal of the learner is to maximize its expected cumulative reward up to a certain horizon, capital T. And the goal is to design algorithms for the learner to maximize this reward. So the learner is initially unaware of its environment, and it learns through its past experience with the environment. So we call the history of the learner as the previous arm selected by the learner and the reward observations corresponding to that arm. So a policy for the learner then needs to take that history into account and map it to a probability distribution over the set of arms. And in round T, the learner is going to sample an arm dictated by its policy and play it. So how do we evaluate the policy of a learner? First, let's consider an oracle that knows the expected rewards of every arm A, mu A. Of course, the oracle can also compute the best expected reward this is just the expected reward of the arm with the highest expected reward, and can always select that arm to incur a cumulative expected reward of capital T times mu star. So over capital T rounds, an oracle can get this much reward. So we can basically evaluate how the policy performs by a measure called regret. The regret measures basically the difference between the cumulative reward of the oracle and cumulative reward of the learner. So every mistake of the learner would make the regret increase. And it is well known that maximizing the cumulative expected reward is equivalent to minimizing the expected regret. So we can measure how the policy performs by measuring this regret and try to design policies that minimize the growth rate of the regret over time. So this problem was investigated by Lyon and Robinson in 1985, and they were able to show that for a general family of reward distributions, any good policy needs to sample each arm logarithmically many times. So there is a lower bound on the performance. And they were also able to show that there exists a policy that attains this lower bound asymptotically. So that means that this is the minimum growth rate of the regret. It needs to increase logarithmically over time when the arms are independent of each other. So how to design a good policy for the learner? So a good policy needs to strike the balance between exploration and exploitation, which is a canonical problem based on reinforcement learning. So a good policy needs to exploit the arm that it believes to be the best, frequently, but in order not to get stuck in a suboptimal arm, it also needs to explore arms to discover the best. So how can this be achieved? Well, there are many ways to achieve this. Today I will just talk about one way, which is related to this talk. It is called the principle of optimism in the face of uncertainty. So what the learner does is that at each round it calculates an optimistic estimate of the reward of arm A, which is called G. G is composed of two terms. Mu hat is the sample mean of the rewards collected from arm A, from the previous plays of arm A, plus an exploration bonus, and this exploration bonus is inversely proportional to the number of times an arm has been selected so far. Then the policy is just to, at each round, select the arm with the highest index. So an arm can have the highest index due to two reasons. Either its sample mean reward is high, that means that we observe good rewards from that arm, or its exploration bonus is high. That means that it is played less frequently than the other arms. And this essentially trades off exploration and exploitation. So it's a known fact that this G is an upper confidence bound for the true, unknown, expected reward of arm A. That means that in all rounds, this G is greater than or equal to mu with a high probability. And the regret of this simple algorithm is analyzed by R et al. in 2002, and it is shown to grow logarithmically over time. So this growth rate matches the minimum possible growth rate. And this is just one simple policy that can achieve the order optimal regret. Any questions so far? Okay. So now I will expand this simple bandit model to allow it to model more complex applications. So one famous extension of the standard bandit is the contextual bandit. In a contextual bandit, the learner at the beginning of each round, before selecting the arm to play, observes a context, or also called sign information, which gives a hint about the rewards in that particular round. So formally, arms reward distributions now depend on the context. They are parameterized by the context. And the goal is to compete with the oracle that takes the best action for each context. So now the history of the learner or the agent is composed of all past contexts observed, all past arms selected, all past rewards observed, and the current context. So a policy now maps this to a probability distribution over arms, and the learner basically plays the arm dictated by its policy. So why is this theoretical model important? Because it has many applications. So let me talk about a few of the applications. First of all, a typical application is recommender systems, where we would like to personalize recommendations based on the features of the users. So one example is, for instance, news article recommendation. Contextual bandits can also be used as an alternative to A/B testing. They are used in web content optimization. Or in personalized healthcare, they are used in personalizing treatments for the patients, and also in clinical trials. Of course, there are also a lot of communication applications. For instance, in wireless communication, we can use them for beam alignment and dynamic rate and channel adaptation and so on. So, what I'm going to present now is an extension of the contextual bandit. This is the work that I did together with my students. So, in a multi-objective contextual bandit, arm rewards are multi-dimensional instead of being single-dimensional. So, in this presentation, I'm going to focus on the two-dimensional case, specifically. So, what happens is that the learner observes a context, it chooses an arm, then it receives two different rewards from the chosen arm. But these rewards correspond to different things. They are apples and oranges, so that we cannot just add them up and give as the final reward. So I will give some motivation now. If you think of patients arriving sequentially over time, and we would like to choose for each arriving patient a treatment, context would be the patient features, arms would be the treatments, and the first objective might be related to the effectiveness of the treatment, and the second objective might be related to the side effects of the treatment. So in this case, we cannot simply add up objective 1 and 2, because they represent different things. In a multi-channel communication example, the context can represent the noisy channel state information. Arms can be transmission rate channel pairs, and objectives can represent different things such as throughput, reliability, and latency. So one important problem in the multi-objective version is that there may not be a single arm that simultaneously maximizes all the objectives. Therefore, we need to find a way to choose arms in order to achieve a trade-off between the objectives. So this will be the main topic of this talk. So the open questions basically are, in the multi-objective setting, how do we define an optimal arm? What is an optimal arm? How do we measure regret? With respect to what benchmark? How fast will the regret grow? So typically we would like to design algorithms that have regret growing sublinearly over time. That means lower than a linear rate of growth. Why? Because if a regret grows sublinearly over time, then the time average regret, as t goes to infinity, would approach 0. which means that we are learning well. Okay, so now I will explain you the main, I will first define the main problem in a mathematical way. And let me begin by stating our contributions in this work. So we are the first to propose and analyze multi-objective contextual bandit. We are the first to study lexicographic optimality and Pareto optimality in a contextual bandit problem. And then we design sublinear regret learning algorithms for this problem. So here is the formalism. We have k arms, k actions. Contexts come from a dx dimensional set. For simplicity, let's take it to be the unit hypercube. Let's focus on the case where we only have two objectives, 1 and 2. Then, given context x, the random reward vector of arm I is sampled from an unknown distribution, f of I, also parameterized by the context. So we are interested in expected performance. Let's define the expected reward of arm I under context x in objective 1 as mu I1 and in objective 2 as mu I2. Of course, the learner is initially unaware of all these quantities, so it needs to learn this by repeated interaction. So at each round, the learner first is going to observe the context of that round. It's going to select an arm, and so we're going to receive a random reward of the selected arm. This is the problem set. Now, let's talk about multi-objective notions of optimality. As I said, the problem is difficult because there may not be a single arm that simultaneously maximizes all objectives. So from multi-objective optimization literature, we have a few different notions of optimality. A common notion of optimality is lexicographic optimality. So given context x, an arm is lexicographic optimal if it is the best arm in the first objective, and among all arms that are best in the first objective, it is also the best in the second objective. So let me clarify this via an example. So assume that for context x, the expected rewards are given like this. This example has 4 arms. So since first objective matters more, I call it the dominant objective, and second objective non-dominant objective. So if you look at these expected rewards, we see that B and C have the highest expected reward in the first objective. Among them, C has the highest expected reward in the second objective. So C is the lexicographic optimal arm, given context x. So for a different context, it is possible that the lexicographic optimal arm is different. And we need to learn that. Then a question that comes to mind is, how bad are other arms? For instance, how bad is arm A? So what we can do is the following. We can look at each objective separately and measure the loss of arm A in each objective with respect to arm C. So if you look at objective 1, arm A has reward 1, arm C has reward 2. So the gap of arm A is 2 minus 1. Okay? But in objective 2, arm A has a higher reward than arm C. So the gap of arm A in objective 2 is here 3 minus 4. It's actually better. So what we do is we keep a separate loss for each objective. But there are other notions of optimality as well. For instance, another common notion of optimality is Pareto optimality. So Pareto optimality means the following. If I switch from one arm to another arm, if my arm is Pareto optimal, then I cannot improve both objectives. So with this definition now, if we look at arm A, if we switch from arm A to any other arm, we will lose in the second objective. Some cases we can gain in the first objective. So that means that arm A is Pareto optimal. And due to the similar reason, arm C is also Pareto optimal. So there are two Pareto optimal arms. Again, it depends on the context. For a different context, the set of Pareto optimal arms might be different, and we need to learn that. And also, it's a well-known fact that the set of lexicographic optimal arms is a subset of the set of Pareto optimal arms. So it's kind of a smaller set. Now, the question is, if we come to the definition of Pareto optimality, how bad is an arm that is not Pareto optimal? For instance, let's put the arms based on their expected reward vectors onto this plane. So A is here, B is here, C is here, and D is here. So what we do is we define a notion called Pareto suboptimality gap to measure how suboptimal is D. And it is defined as the minimum amount that we need to add to each coordinate of the expected reward of B such that it becomes not strongly dominated by any other arm. So in this case, it turns out that if we add 2 plus a small amount, we are guaranteed. That means that the Pareto suboptimality gap of D is 2. So arms then that are closer to the Pareto optimal arms are expected to have smaller Pareto suboptimality gaps. Okay. Now we define two notions of optimality that we can use. And we can try to identify arms that satisfy, say, these notions of optimality. But let me also talk about another approach to this problem, which is called scalarization. It's also a well-known and well-conceived approach. So the idea is the following. Although I have multidimensional rewards, I can define some scalarizing weights. These weights basically tell the trade-off between different objectives. And I can project the expected reward vector on the real line and define a scalar expected reward. Then I can run a bandit algorithm with the scalar rewards to minimize the scalarized regret. Well, this approach has some limitations, and I will mention them. First of all, we are considering a learning problem. That means that we don't know the expected rewards of the objectives. So the weights give us how we trade off these rewards. So without knowing the expected rewards, it is unrealistic to assume that we know the weights that will achieve the optimal trade-off between these rewards. Moreover, these weights can also be dynamically changing over time. And also, in multi-objective problems, it might also be possible that the decision maker's mechanism does not involve scalarization at all. For instance, if we go back to the personalized treatment example, different doctors or patients might have different preferences over the set of Pareto optimal treatments, so that their preferences cannot be captured by a single scalarization. So due to this, in learning we take the approach of treating the problem as a multi-objective problem without scalarizing it. And there are two ways we motivate the to look at the Pareto front. Basically, in the first Pareto approach, what the learner does is it provides a set of arms, say an estimated Pareto set, at each round. And the user served in that particular round is going to see these options and, based on its own preference, pick an option, pick an arm from that recommended set. So then we can say that this recommendation is good if the actual Pareto set is a subset of the set that we recommended, and if all the recommendations have a small Pareto suboptimality gap. So here we leave it to the user to make the choice from the Pareto front. So another approach could be the fair Pareto approach. In this case, the learner can treat all arms in the estimated Pareto set equally. So it can select an arm from the estimated Pareto set uniformly at random. And that recommendation would be good if its Pareto suboptimality gap is small. And if such a recommendation ensures that the number of plays of arms in the actual Pareto front have a small variance. For instance, if you think of using this to recruit patients for a clinical trial, it would be fair to treat all patients who would benefit from the clinical trial equally. Okay, so with the lexicographic and Pareto optimality notions, now let's define how we can identify the learning performance. So for lexicographic optimality, we propose a regret notion called lexicographic regret. So consider an arbitrary fixed sequence of contexts. So we don't assume any structure on how the contexts arrive over time. And the lexicographic regret is a multidimensional form of regret. Basically what we do is we measure the regret of the learner with respect to the lexicographic optimal arm given the contexts separately in each objective. So this measures how bad the learner performs with respect to a policy that always picks the lexicographic optimal arm given context in the first objective and in the second objective. For the Pareto optimality case, we define a notion called the Pareto regret, which is a scalar regret. And this measures basically the sum of the Pareto suboptimality gaps of the arms chosen by the learner. And our goal is to design algorithms, learning algorithms, whose time average regrets go to 0. Okay. Well, unfortunately, if we don't make any further assumptions on how contexts arrive or the set of contexts that can arrive, achieving this sublinear regret may not be possible. For instance, consider a case where X is infinite, the set of contexts is infinite. It is possible that at every round a new context arrives. That means that we need a way to leverage the past information in order to guide our decisions for the current context. So we need more structure on the problem. Okay, so a common and natural structure is what is called similarity information. So what similarity information tells is that an arm has similar expected rewards in all objectives for similar contexts. Basically says that the expected reward of an arm in each objective is ellipsis continuous in the contexts. Well, now this, if we know this information now, we can leverage past information to guide our future decisions. So the idea is very simple. We can learn by grouping similar contexts. We can identify similar contexts in the past and use their observations obtained under these contexts to choose our action for the current context. Now, with these definitions, I will go and describe you a method that is able to achieve low lexicographic regret. So I'm going to show you an algorithm. The algorithm is called MOPMAP. This algorithm uses a very simple method to leverage past information, but it uses a smart method to trade off exploration and exploitation. So I will explain the algorithm in a simple case where the context set is the unit interval. So at every round a context arises from here. So the algorithm to learn by grouping similar context partitions X into M intervals like this. So you can see that here. And what it's going to do is it's going to use the past information in each interval to form reward estimates within that interval. Okay. So when a context comes in round T, it's going to identify which set the context belongs to, and then uses the estimates obtained in that set as a proxy to the true unknown expected reward to make decisions. Of course, as you see, this looks like a discretization and it introduces some approximation errors. But thanks to that similarity information, we know that the errors are only proportional to the length of the interval. So what we can do is that, based on our time horizon, we can adjust our M, our discretization level, to have some regret guarantees. So from now on, I will explain this smart exploitation part. So I will focus on what happens after the learner identifies the set that the current context belongs to. So all the quantities that I will talk about, all the estimates will be related to that particular set that the current context belongs to. First of all, let's talk about the uncertainty we have in the estimate of the Arm's rewards. So we don't know the true expected reward. We have a sample expected reward, an empirical average of the rewards collected so far. So consider a particular arm and a particular objective. We can define an upper confidence bound, G, which is nothing but the sample mean plus an uncertainty term. And a lower confidence bound, which is just sample mean minus the uncertainty term, denoted by L. So our uncertainty comes from two sources. One is the uncertainty due to discretization, which was in the previous slide, and it's proportional to 1 over M. The other is the uncertainty due to noise observations, finite number of noise observations, that is proportional to 1 over square root of number of times arm A has been selected within that particular set. So using this upper confidence bound and lower confidence bound, we can construct a confidence interval for A in each objective. Here I just show it for objective 1, centered around the sample mean estimate. So it looks like this. Now what we can show is that in all the rounds, the true expected reward of the arm given the context of that round is in this confidence interval with a very high probability. So this will guide us to develop an algorithm that will be able to trade off exploration and exploitation. First of all, the classical approach that I described, which is the optimism in the face of uncertainty, unfortunately does not work in the multi-objective problem, because if we try to apply it by, say, dictating that we always select the arm with the highest upper confidence bound in objective 1, that means that it does not look at objective 2, so that it can incur linear regret in objective 2, which is something that we don't want. So what we propose is to tolerate some suboptimality that is proportional to uncertainty in the first objective to try to identify lexicographic optimal arms. So what we do is, first we calculate the optimistic best arm in the first objective. Let's call it A star. That is the arm with the highest upper confidence bound in the first objective. Here you see the confidence interval of the optimistic best arm in the first objective. And the idea is the following. Assume that I have another arm B, and B's confidence interval in the first objective is like this. So what I know from the previous slide is that the true expected reward of arm star is somewhere here, but I don't know where. And the true expected reward of arm B is somewhere here. I don't know where. So with this, since the confidence interval of arm B overlaps with the confidence interval of arm star, there is a chance that the true expected reward of arm B in the first objective is higher than arm star. Maybe it is here, and arm star is here. So in this case, true expected reward of arm B would be higher in the first objective. So that means that there is a chance that this arm B is indeed the lexicographic optimal arm. So now what we do is we create a set of candidate optimal arms, and we include all arms whose confidence intervals in the first objective overlap with the arm stars in this candidate set. But if we have an arm C like this, we know that arm C's expected reward is somewhere here, and with a high probability it has no chance of being greater than arm star's expected reward. So that we don't include arm C in the candidate set of optimal arms. So the idea is, after forming this candidate set of optimal arms, how do we choose an arm from that set? Well, for instance, can we now just look at the upper confidence bound, the optimistic estimate in the second objective, and choose the arm with the highest upper confidence bound in the second objective from all candidate arms? But it turns out that this also does not work. And the reason for that is that in this case, the uncertainty of the optimistic best arm in the first objective may not decrease. That means that the set of candidate optimal arms, if we do this, may not converge to the set of lexicographic optimal arms. So we were able to solve it then by proposing another way of exploration and exploitation. What we do is we force reducing the sample uncertainty of the estimated best arm in the first objective when it is high. That means that if its sample uncertainty is greater than its uncertainty due to discretization, we force selecting the optimistic best arm in the first objective. And if this is not the case, then we do our usual selection. And we were able to prove that this works. And recall that dx is the dimension of the context set. So we adjust the amount of discretization based on the time horizon and the dimension of the context set like this. Then the algorithm that we propose is able to achieve a lexicographic regret that is of this order in both objectives, and a Pareto regret that is of this order. So as you see, the exponent of time here is less than 1. That means that the regret is sublinear. So in terms of the average regret, as t goes to infinity, we expect these to converge to 0. So that means that in average we can get as good as the order. Okay. But you might ask where these constants come from, and is it possible to achieve maybe a smaller regret, right? So there's an interesting observation. If we choose our discretization slightly different, then this makes the regret in the first objective like this, slightly lower than what is in the theorem. And for the single objective case, this is order optimal. That is the best can be achieved. But this results in a very bad performance in the second objective. And the Pareto regret also is good in this case. Best for the single objective. Well, then it happens to be that there is a fundamental difficulty in the problem. That means that learning lexicographic, to minimize the lexicographic regret, is fundamentally more difficult than learning to minimize the Pareto regret. And in one of our recent works, actually, we were able to show this, that lexicographic regret is harder to minimize. so that we have a higher order of the capital theta. Okay, so I'd just like to conclude this part by showing some experimental results. So what we did here was we compared our algorithm with another algorithm, a learning algorithm which only tries to optimize the first objective, and try to compare their regrets separately in objective 1 and objective 2. As it appears, our algorithm achieves a little bit higher regret than the other algorithm in the first objective, since it's not just trying to minimize the regret in the first objective. But the advantage of our algorithm comes when we look at the second objective. In the second objective, our algorithm's regret is much smaller than the other algorithm. Of course, we don't expect much from the other algorithm because it is only trying to optimize the first objective without dealing with the second one. Okay. Alright, so now I talked about how to achieve lexicographic optimality. Let me also talk about how we can achieve Pareto optimality in a fair way. So, we would like to improve learning and answer the following questions. Instead of that simple discretization of the context set, can we find an adaptive discretization that exploits the geometry of the reward surface such that it can adapt and learn faster? Or instead of dealing with a finite number of arms, can we handle an infinitely many and a high-dimensional set of arms? So, previously we minimized lexicographic regret. Of course, this also minimized the Pareto regret because lexicographic optimal arms are also Pareto optimal. But the question is, can we minimize Pareto regret and ensure fairness over the Pareto optimal arms somehow? So in the remainder of my talk, I'll just briefly touch upon these topics and show that we were able to have an algorithm, design an algorithm that achieves these objectives. So I'm going to describe the algorithm. It's called Pareto contextual zooming. It uses a well-known idea called contextual zooming in the multi-objective case. So I'm going to illustrate how it works by a very simple setup where we have one-dimensional context and one-dimensional arm set. Okay, so X is the context set, Y is the arm set. And consider that the unknown set of Pareto optimal context arm pairs lie here. So the idea is now, instead of having a prior fixed uniform grid to discretize, we adaptively discretize the joint context arm set. And we will try to fairly select arms from an estimated Pareto set. So the algorithm proceeds over rounds. It creates balls that cover the joint context arm set. And it keeps a summary of the past observations in each ball. Basically, it keeps a sample mean estimate for the rewards in that ball and an upper confidence bound for that, for every objective. So as time goes on, this algorithm is able to zoom into interesting regions of the joint context arm set. Basically, when there are too many arrivals to a ball is split into smaller balls. So this allows us to do more refined exploration. And with this, balls concentrate on regions with frequent context arrivals and low Pareto suboptimality gap. So when new context arrives, what we do is we identify balls that contain that context and compare upper confidence bounds of these balls to identify Pareto optimal balls. So assume that in this case, the Pareto optimal balls are like this. And here it is up to us how to make our recommendations. For instance, one thing that we can do is, in the Pareto approach, we can recommend all the set of arms in the estimated Pareto set and leave it to the user to make its final choice. Or we can choose an arm uniformly at random from this set to treat all the estimated Pareto optimal arms in a fair way. So again, property of our algorithm is that if we define this quantity as an R approximate Pareto front, that is Pareto front, it includes the Pareto front but also some arms that are close to the Pareto front, our algorithm ensures that the Pareto suboptimality gap of the arms selected by the algorithm is bounded by the radius of the selected balls with a high probability. And we were able to show that for our algorithm, we achieve a Pareto regret that is has this order. It is actually the optimal order. Where here this quantity dp is Pareto zooming dimension. It is related to size of the R approximations of the Pareto front. And usually it is much smaller than the sum of the R and context dimensions. So we are able to design an efficient algorithm for this problem as well. But let's try to see how it performs in practice. So consider a simple experiment where context is X dimension, R is Y dimension, and here you see the expected reward in objective 1, here you see the expected reward in objective 2. And this setup exactly corresponds to a Pareto set that looks like this. So to evaluate the performance, basically the fairness of our algorithm, what we do is the following. We divide the Pareto set into these 6 beans and try to record the frequency of times an arm from each bean is played. So if our algorithm is fair, it needs to put an equal share to each bean. So here are the results. We compare our algorithm, blue, with another algorithm, contextual zooming. The contextual zooming algorithm only optimizes the first objective. And we compare these algorithms in terms of the fraction of times these Pareto beans are played. As you see, our algorithm almost equally plays these Pareto beans, whereas the other algorithm, of course, as we expect, because it does not optimize objective 2, just puts an unequal share to each of these beans. On the other hand, their performance in terms of regret and is almost similar. Okay. So what are the conclusions? Basically, we established models and algorithms for multi-objective contextual learning. In the meantime, we showed that minimizing lexicographic regret is fundamentally more difficult than minimizing Pareto regret. And we were able to handle infinitely many arms and context as long as there is a similarity structure that allows us to leverage past information. So I will conclude my talk by giving a few feature research directions. First of all, in this talk, I define the Pareto front in terms of the instantaneous rewards. That is the expected reward for each round. But an interesting approach, another approach would be to define the Pareto front in terms of the cumulative rewards. Another feature research direction is combinatorial multi-objective learning, in which many open problems exist. So I'll describe you what this combinatorial means by describing a combinatorial bandit problem. So in a combinatorial bandit, in every round, instead of selecting one arm, the learner selects a subset of arms. It is possible that some of the selected arms trigger other arms. And as a result, at the end of the round, a random triggered set is observed, together with the outcomes of the arms in that set. And the total reward that the learner receives is a function of the outcomes of the arms in the triggered set. Again, this problem has many interesting applications. One is online influence maximization problem. Here we are given an influence graph. There are vertices, there are edges. And there are weights on the graph, and the weights are influence probabilities that are unknown. So you can think of this like maybe a Twitter graph. So in each round, the learner selects a seed set of nodes. These nodes spread the influence over the network according to some influence propagation model. Then we observe at the end of the round who influenced whom and get as reward the number of influence nodes. For instance, one example of this is viral marketing. And the goal is to maximize the number of influence nodes over T rounds. So this is a combinatorial bandit. So another well-known example is the cascading bandit, especially used in ranking items, where in each round we show a list of items to a user. The user scans the list from top to down and clicks on the first attractive item. It's like when you search something, right? A list of alternatives come, you scan from top to down and click on the first attractive, say, link. And here is the goal is to maximize the number of clicks over T rounds. So these two problems are special cases of this combinatorial bandit. So we have some recent progress on the combinatorial bandits. In the scalar case, we define a contextual combinatorial bandit and solved it in the concept of influence maximization. And then we also proposed and analyzed Thompson sampling, a Bayesian algorithm for the combinatorial bandit. But there remains much to be done to merge combinatorial bandits with multi-objective optimization. So the main challenges are, even the single objective case, most of these combinatorial optimization problems are NP hard. And in the multi-objective case, they are even harder than that. And most of the practical single objective bandit algorithms in the combinatorial case rely on existing approximation oracles for the offline problem. So not much exists for the multi-objective case. Moreover, if we consider notions like Pareto Optimality, in this combinatorial case, there might be exponentially many Pareto optimal solutions, which again will create a problem. So these are all challenges that needs to be addressed in the future. So I'd like to conclude my talk here, and I'd be happy if you have any questions.